Okay, ladies and gentlemen, welcome to the lecture on DSP, Digital Signal Processing, EC 393. Today, in our lecture, we shall be studying about the continuous time Fourier transform, continuous time Fourier transform for aperiodic signals. Okay. Now then, in the previous lectures, we have studied about the Fourier series, which was evidently used for the conversion of a time domain continuous signal to the frequency domain. But in our case, in the Fourier transform operation, which is quite similar to that of the Fourier series operation, it is similar in some regards, because in this operation we shall also be converting the time domain signal into the frequency domain signal, whereas in case of Fourier series we used the continuous time signal, I mean the periodic signal, and in case of Fourier transform we shall be using aperiodic signal. So its utility in other sense can be stated as the Fourier transform is used to convert time domain signal to frequency domain and is essentially utilized for aperiodic signals. Now, without a further ado, let us go to the derivation of the synthesis and analysis equation for the continuous time Fourier transform. So, the derivation of synthesis and analysis equation of CTFT, continuous time Fourier transform. Okay, ladies and gentlemen, first of all, we consider an aperiodic signal. An aperiodic signal, say it to be x of t, which looks something like this. Say this is our signal, the time axis t, the signal x of t, and say this point be Tp over 2, negative of Tp over 2, and this one being Tp over 2. Of course, this signal is aperiodic for a finite time duration. Now, if you observe carefully, this signal x of t can be considered to be a periodic signal, say xp of t with a time period of Tp. Now, how can we achieve this signal xt of p? Say, for instance, if we take the signal x of t, say this signal, and repeat it after every Tp time, so this becomes Tp, this becomes negative of Tp. So the signal x of t becomes periodic if we shift the signal for every time period Tp. I hope that is clear. So now it is quite clear that if we are to make this signal x of t to a periodic signal, we do nothing, just take this value, this triangular value, and repeat it after every tp, that means the time period, time along the time axis. Now mathematically this can be written as x of t is equal to limit when tp goes to infinity x of p t. So xp of t is the periodic signal. So if we take a limit such that the time period becomes infinity, that means from this point to this point becomes infinity. So the signal looks something like this. This tp point will occur at infinity. So evidently what we get is that this signal is equal to this signal. So what I mean to say is that when the time period goes to infinity, the signal becomes aperiodic. Now, if we recollect the synthesis equation for CTFS, the synthesis equation for continuous time Fourier series, we get xp of t, working with the periodic signal xp of t, because the Fourier series is applicable for periodic signal, will give us k, which goes from minus infinity to infinity, and gives a running sum of ck, being the Fourier series coefficient, e to the power j twice pi k f naught t, where obviously f naught equals 1 over tp. And otherwise we can write from the analysis equation, the analysis equation will give us the value of ck in terms of the signal xp of t. So ck is equal to 1 over tp, that goes from minus tp by 2 to tp by 2, xp of t e to the power minus j twice by k f naught t dt. Now, it must be mentioned that xp of t, that is our periodic signal, will become the aperiodic signal x of t will be equal to x of t for the condition for minus tp over 2 less than equal to t less than equal to tp over 2, which essentially means that if we consider for this range to this range, only from this value to this value, we get only one part of the signal. In other words, if I show it in this figure, these 2 points are minus tp over 2 and this is tp over 2. If we take the value from this range, we get only this part, and the signal is essentially equal to that of the aperiodic nature. So keeping that in mind, the equation can be written as ck equals 1 over tp, goes from minus tp over 2 to positive tp over 2, x of t, because as we have established, for within this limit xp of t will be equal to x of t. I have changed xp of t over here to x of t, e to the power minus j twice by k f naught t dt. Now if you observe closely that in this signal x of t, if we go beyond this point x in the time axis tp over 2, that means in this direction and this direction, the value of x of t from this point onward is 0, and from this point onward is also 0. So if we change the limit of this integral to minus infinity to infinity, it essentially doesn't change the value or the result of the integral that will determine the value of c of k. So x of t will be equal to 0 when modulus of t will be greater than equal to tp over 2. That is, in other words, we can say that minus tp over 2 will be greater than t and tp over 2 less than t. So under these conditions, we say that ck becomes 1 over tp, changing the limit from minus infinity to infinity, because in the previous integral we have taken the limit from tp by 2 to minus tp by 2, that is from this point to this point. And for any other point outside this two range, the integral, that means the area under this curve, will essentially be 0. Hence, if we change this limit from infinity to negative infinity to infinity, what happens is that the value doesn't change because we only get this part. So if we extend this to negative infinity, there is no value of x of t over here. And similarly in this side, there is also no value of x of t for the positive infinity. So if these limits are changed to negative infinity and infinity, all we get is only this portion of the curve. Hence, moving forward, x of t e to the power minus j twice by k f naught t dt. Let us mark it as equation number 1. Now let us define a function x of f. Let us define a function capital X of f, which is to be called the Fourier transform of x of t. So x of f will be equal to minus infinity to infinity x of t e to the power minus j twice by ft dt. Let's mark it as equation number 2. So there is no relation between equation 1 and 2. We have written the part that is the right hand side of equation 2 simply from the definition of the Fourier transform. Now it is evident that x of f is a function of the continuous variable f. That is, x of f is a function of this variable f, and whatsoever is not dependent on our period, that is Tp, or the frequency f naught. So comparing 1 and 2, we get ck to be equal to 1 over Tp x of k f naught. Since in this case the variable was t, and in our case in the equation 2 the variable becomes f. So replacing this part of the equation, 1 over Tp becomes remains as it is, and this part, which can be written as x of f, from here it becomes x of k of f naught, where this is our operating variable. So upon further simplification, we get Tp times Ck is x of k by f naught, which equals x of k by Tp. Obviously, f naught is equal to 1 over Tp. Now, substituting this value of Ck in the synthesis equation, substituting the value of Ck in the synthesis, we get xp of t to be equal to 1 over Tp, a running sum where k goes from minus infinity to infinity, x of k over Tp e to the power j twice pi f naught t times k. Now then, for Tp to be approaching to infinity, let us define the frequency, fundamental frequency f naught to be equal to del f to be equal to 1 over Tp, and hence xp of t becomes summation of k, which goes from minus infinity to infinity, x of k, instead of f naught we are writing delta f e to the power j twice pi k del f t times del f. For this value of 1 over Tp, we write del f. Now then, ladies and gentlemen, before moving any further, I would like to concentrate on the fact that the derivation of the Fourier transform is quite heuristic. That means it is not mathematically chronological, rather than we have to derive it quite intuitively. And the next part, which I am going to explain, might be a little hazy, but I'll try my best to make it clear to you. As we have seen before, when Tp goes to infinity, right over here, when Tp goes to infinity, xp of t will be equal to x of t. So xp of t will be equal to x of t. And del f can be replaced by a differential variable df, which is for continuous change. Now then, since we have changed since we have considered for the limit, and the limit occurs for a continuous value of Tp which goes to infinity, we must convert this summation over the discrete value to a continuous value, and hence delta f will change to df. The summation operator will become an integral, and k del f will become the continuous variable f. So we can write limit of Tp which goes to infinity xp of t will be equal to x of t, which is equal to limit del f, which goes to 0. Now, why this limit del f goes to 0? Because we have seen that f naught equal to del f equal to 1 over Tp, which is shown over here. So if Tp goes to infinity, of course del f will move to 0. Hence we give this limit del f tends to 0. We take the running summation, k summation of minus infinity to infinity, x of k delta f e to the power minus j twice by k delta f t del f. I'm sorry. Now, from the intermediate concept, we have seen that the integration is essentially the area under a curve. And say this curve is divided into various rectangular bodies like this one, this one being 1, 2, 3, 4 and n. So in order to get the integration of this curve, we have to add the area of these individual rectangles until the value of n. So integration of this curve can be written, if this point being a to b, summation of, where I goes from 1 to n, x times I, x of I times del t. X of I being this value, the length of, I'm sorry ladies and gentlemen, it's becoming very haphazard. Let us draw it clearly. So this being our curve, so this is x of t. We take various rectangles. And finally this value, this is 1, 2, 3 and nth. So the length of this rectangle along the y-axis is x, and along the time axis its breadth is delta t for every rectangle. So what will be the area under this curve? Will be the summation of the area of each of the rectangles, which goes from 1 to n, x of I for the operator, that is 1, 2, 3, that is the I being the variable for every rectangular change, times delta t, and n will always be, if the limit is a to b, will be b minus a over I. Now, if we take the limit of n becoming infinity, that means the number of divisions becoming infinite time and the value of del t becoming infinitesimally small, we can write 2n x of I times del t to be equal to integration of x dt, which is what we are going to do over here. So if del f tends to 0, this value can be written as an integral. But you have seen here n goes to infinity, but here del f is going to 0. So will this be applicable for this formula? If you look upon closely, the relation of del f, that is the frequency and time is inversely proportional. So since in this case we were operating in the time axis where n goes to infinity, in our case for del f tends to 0 essentially means the same thing. So finally we can write x of t to be equal to minus infinity to infinity x of f e to the power j twice by f t df. This relation is known as the inverse Fourier transform. So, upon summarizing, we get the synthesis equation. We get the synthesis equation where x of t equals to minus infinity to infinity x of f e to the power j twice by f t df, which is the inverse transform, and the analysis x of f to be equal to minus infinity to infinity e to the power minus j twice by f of t dt, which is the direct transform. So I hope up to now it is clear, although as I've mentioned before, the derivation is not mathematically chronological, rather heuristic in nature. That means the relation is quite intuitive. So it cannot be derived by pure mathematics of calculus or the integrals or any other form of chronological mathematical operation. Rather, what we have to do is to think about the concept and derive for the direct and the inverse transform. Okay, with that we complete the derivation of the Fourier series, the Fourier transform, that is the inverse transform and the direct transform. In the next part we shall be studying about the various properties of the continuous time Fourier transform.